All right, folks, buckle up because we're about to dive into some serious AI research.
Ooh, sounds intense.
We're talking high-level math, the kind that usually lives in academic papers, not exactly light podcast listening.
All right, I'm intrigued. What kind of math are we talking about here?
Well, we're going to be looking at AI that can understand mathematical concepts, solve some pretty complex problems, and get this, even prove theorems.
Whoa, hold on. So we're not just talking about AI that can crunch numbers faster than us humans, right? This is about AI actually understanding math on a deeper level.
Exactly. And the model that's making waves right now is called DeepSeekMath.
DeepSeekMath. Okay.
It's open source, which is pretty unusual because it's actually outperforming a lot of the larger closed source models on some pretty challenging math tasks.
It's like the David and Goliath of AR, huh?
You got it.
But what's their secret weapon? Is it the algorithms or the training data or what?
Well, it's a bit of both, actually. The researchers behind DeepSeekMath knew that data was absolutely key.
Makes sense.
So they started with this data set called Open Web Math.
Open web math.
Yeah, it's a collection of, high-quality math content that they pulled from the web, but even that wasn't enough.
So where did they go from there? Did they tap into some secret math archive or something?
Not exactly a secret, but definitely massive.
Okay.
They turned to the Common Crawl.
The Common Crawl.
It's basically a giant digital library of, well, the entire internet. We're talking billions of web pages.
That sounds less like a data source and more like a data nightmare, honestly. How do you even start to find the good stuff in all of that?
Right. Well, this is where it gets really clever. They developed this whole filtering pipeline, and it combines some automated tools with, actual human expertise.
Okay, interesting.
So they used this tool called fast text.
Fast text.
Yeah, to identify pages that were, math related. But they went a step further. They started looking at entire website domains.
Whoa, so instead of looking for a needle in a haystack, they were looking for haystacks full of needles.
Exactly. So, if a domain had tons of pages about calculus, algebra, geometry, all that good stuff, it was a pretty safe bet that the whole domain was mathematically rich.
That's pretty clever.
And get this, they even brought in human annotators to double-check specific URLs,
Wow.
making sure they were really getting the highest quality math content.
They were serious about this.
Oh yeah, they repeated this whole process 4 times, refining the filtering each time. And the result was pretty impressive. They ended up with a data set of 35.5 million web pages, which totals, get this, 120 billion math tokens.
120 billion? That's got to be way bigger than any previous math-focused data set, right?
It dwarfs them. It's called the DeepSeekMath corpus.
DeepSeekMath corpus. I'm starting to see why the model is punching above its weight. But how did they go from this massive data set to a model that can actually do math?
Well, that's where things get even more interesting. DeepSeekMath isn't built from scratch. It actually starts its life as a model called DeepSeek Coder Base v1.5.
Coder, is there a connection between coding and math here?
You're catching on quick. It's something that surprised even the researchers, to be honest. It seems that pre-training on code data actually makes the model better at mathematical reasoning.
That's fascinating. I guess code is all about logic and problem solving, just like math is.
Right? It's like training on code gets the model thinking in a more structured, mathematical kind of way.
Makes sense. So they took this code-trained model, fed it this massive DeepSeek math corpus. That's a good start, but there's got to be more of the story, right?
Oh, there's always a twist. They also included data from some other sources like Algebraic Stack. And then there's Arxiv, which is this huge repository for scientific papers.
Okay, so I would think training on Arxiv with all those complex math proofs would be like the ultimate brain boost, but I have a feeling you're about to tell me that it didn't work.
You know me too well. Training on the Arxiv papers actually didn't improve DeepSeekMath's performance at all.
Whoa, seriously?
Yeah, it kind of goes against a lot of the assumptions in the field. It suggests that the data source and the quality of the data are even more important than we thought.
That's really interesting. So we've got this massive, carefully curated data set. We've got a code-trained model. What's the next step in this whole mathematical evolution?
Well, they actually developed 3 versions of DeepSeekMath, each building on the last. So first you've got DeepSeekMath Base.
DeepSeekMath base. Okay.
That's the foundation, the one we've been talking about. Then they fine-tuned it to create DeepSeekMath Instruct.
Instruct, as in giving it instructions on how to solve math problems.
Exactly. They trained it on tons of example problems and solutions. And they even incorporated these techniques like chain of thought and program of thought prompting.
Oh, yeah, chain of thought prompting. That's like you're teaching the AI to think step by step, right? Kind of like a human would solve a problem.
You got it. And program of thought is similar, but instead of a chain of thoughts, you guide the model to actually generate a computer program to solve the problem, which again ties back into that whole coding background.
Right, right. So foundational model fine-tuned with specific instructions. What's the third stage in this DeepSeek math saga?
That would be DeepSeek Math-RL, RL stands for reinforcement learning.
Oh, okay. Now we're getting into some serious AI territory. Isn't that how they trained AlphaGo to, beat the world champion at Go?
That's the one. But before we get into the nitty-gritty of reinforcement learning, let's take a step back and unpack what that really means, especially in the context of language models.
Okay, yeah. Reinforcement learning is fascinating, but it can be kind of a head scratcher.
It's not as complicated as it sounds. Think of it like training a dog with treats. You were saying something about training a dog, right? With treats.
Yeah, I'm curious where you're going with that analogy.
Okay, so imagine you're teaching your dog a new trick, right? Every time they get close to doing it right, you give them a treat.
Right, positive reinforcement.
Exactly. That treat, that's the reward. And it reinforces the behavior that you want. And that's essentially how reinforcement learning works in AI.
So instead of a treat, we're giving the AI like a digital pat on the head when it gets closer to solving a math problem correctly.
That's the idea. And the most common type of reinforcement learning used with these language models is called Proximal Policy Optimization, PPO for short.
PPO, okay.
It's been super successful, but it can be really computationally expensive. It uses a separate model. They call it a critic model.
A critic model.
Yeah, and it's used to estimate how good the AI's attempts are.
So it's like having another dog watching the first dog, judging its performance.
Haha, yeah, perfect analogy. But you can imagine having two models working together like that. It takes a lot of computing power, a lot of time.
Makes sense. So that's what GRPO comes in, right?
Bingo.
This is the algorithm developed by the DeepSeekMath team, right?
Yep.
Is it kind of like PPO, but more efficient?
Exactly. GPO takes a different approach. Instead of relying on that separate critic model, it gets a little bit clever.
Okay, how so?
Well, it estimates rewards based on the performance of a whole group of outputs that are generated for the same problem.
So instead of one dog trying the trick, you've got like a whole pack of dogs and are all competing for the treat.
Haha, love it. And by comparing the performance of all the dogs, so to speak, GRPO can figure out which solutions are better. And it doesn't need that second computational expensive critic model.
That's a really elegant solution, like a built-in peer review system for the AI.
And because it ditches that critic model, GRPO is way faster and more efficient. But the real test is, does it actually lead to better results?
Well, you seem pretty excited about it, so I'm guessing the answer is yes.
You know me too well. The researchers actually found that GRPO significantly improved DeepSeekMath Instruct's performance,
Interesting.
even though it was trained on a relatively small subset of the data.
Wait, less data but better results. I thought in AI, more data was always better.
That's what's so intriguing about this, right? It challenges a lot of the assumptions you have in the field. It seems that data quality and clever training methods can sometimes, trump sheer data quantity.
That's a really important point, especially with this trend of building, ever larger AI models. Maybe we need to be focusing more on smarter training techniques and less on just hoarding tons of data.
I think you're absolutely right. And GRPO is a perfect example of that. But, all this talking about training and algorithms, it's just part of the story. The real proof is in the pudding, as they say.
Right. How did they actually test DeepSeekMath's mathematical abilities? Did they, give it an AI equivalent of a math exam?
Kinda. They put it through a whole battery of tests. They used a bunch of different benchmarks that are designed to, measure its mathematical skills.
Benchmarks, those are like standardized tests for AI, right? Let researchers compare different models.
Exactly. And they tested DeepSeekMath on everything. I mean, from grade school math problems all the way up to college level math, even formal theorem proving.
Wow, so they really threw the whole textbook at it, huh?
They didn't hold back. They used GSM-8K, which is a collection of word problems they give to 8th graders.
Okay.
Then they kick it up a notch with the math benchmark. It's considered like competition level in terms of mathematical reasoning.
So they really wanted to see if this AI could, handle problems that would stump a lot of humans.
Oh, for sure. They even included benchmarks based on the SAT, and get this, real MIT college math courses.
Wow, okay, they gave it the ultimate math challenge. So how did DeepSeekMath do?
Well, this is where that underdog story really shined. It consistently outperformed other open source models on these benchmarks.
Impressive.
It even rivaled some of the best closed source models out there, like Minerva 540B, which is way bigger.
So despite being smaller, DeepSeekMath is holding its own against the big leagues.
Absolutely. And it's not just about overall performance either. DeepSeekMath is particularly strong in Chinese math.
Oh, interesting.
Which makes sense because they included non-English data in the training, right? Highlights the importance of diverse data for building, truly capable AI.
Absolutely. If we want AI that reflects the breadth of human knowledge, we need to train it on data that reflects that breadth as well.
Right. DeepSeekMath is a testament to that. But its capabilities go beyond just, crunching numbers. They also tested it on something called informal to formal theorem proving.
Okay, now that sounds intense. What is that exactly?
It's the ability to take a mathematical statement that's written in plain language, human language, and then translate it into a formal proof. using all the mathematical symbols and logic.
Ah, so like taking a human readable explanation and converting it into something a computer can understand and verify.
Exactly. And DeepSeekMath showed some real promise in this area, suggests that it's not just solving problems, it's starting to actually grasp the underlying mathematical concepts.
That's really impressive. It's one thing to like calculate an answer, but it's a whole other level to understand the reasoning behind it. So this brings us to the bigger picture, right? What does all this research mean for the future of AI and math?
That's the million-dollar question, isn't it? The implications are huge, potentially. For starters, the fact that they made DeepSeekMath open source is a game changer.
Yeah, open source is always a big deal in AI.
It fosters collaboration, allows others to build on the work that's already been done.
Exactly.
Open sourcing DeepSeekMath could accelerate research in AI and in math. It's like giving the entire field a booster shot.
And it's not just about research. Think about the potential applications, education, scientific discovery, even everyday problem solving.
The possibilities are really mind-boggling. Imagine students who are struggling with a concept, right? They can use DeepSeekMath to work through problems, get instant feedback on their logic, even explore different approaches to solving it.
Yeah, it could make learning much more interactive, more engaging.
And think about the students who might not have access to the best teachers, the best tutors. DeepSeekMath could level the playing field, right? Give everyone access to a world-class math education.
It's like a democratization of knowledge, powered by AI.
But education is just the beginning. What about scientific research? Math is the language of science, and AI that can speak that language fluently could be revolutionary.
Oh, absolutely. Scientists are drowning in data these days. DeepSeek Math could help them analyze all that data more efficiently, maybe even find patterns that would have been missed by humans.
Right. And it could help them generate new hypotheses.
And remember, DeepSeek Math doesn't just crunch numbers, it actually understands the concepts. So it could help scientists come up with more sophisticated theories and models.
It's like having a research assistant who can not only analyze the data, but also contribute to the whole intellectual process of scientific discovery.
That's amazing. And of course, we can't forget about all the industries that rely on math, like finance, engineering.
Financial modeling, risk assessment, algorithmic trading, all that stuff could be revolutionized by an AI that can really understand complex financial data.
And in engineering, you could use DeepSeek Math to, optimize designs, simulate complex systems, maybe even automate some engineering tasks.
Imagine buildings that are more structurally sound, airplanes that are more fuel efficient.
It sounds like there's no area of human endeavor that wouldn't be touched by this technology in some way. But with all this talk of potential benefits, I think it's important to talk about the potential risks as well.
Oh, absolutely. Any powerful technology can be used for good or for, not so good. And AI is no exception. We got to be mindful of the downsides and work to mitigate them.
Well, one obvious concern is job displacement. If AI can do the work of, human mathematicians, what happens to those people?
It's a valid concern for sure, and it's one that we need to address. But I think it's also important to do with it. AI is a tool.
Right.
It can augment human capabilities, not necessarily replace them entirely.
Kind of like, the invention of the calculator. Didn't get rid of the need for mathematicians, it just freed them up to tackle.
Hey there. Want to share your thoughts on this?
Hey there, can we explain the unified paradigm?
Absolutely. It's a great question, and it's a really key part of this whole DeepSeek math story.
Yeah, it's like the underlying framework that helps us understand all the different training methods. So let's unpack that a bit.
Okay, so Gregory, we talked about how the researchers came up with this idea that all training methods can be broken down into three main parts.
Data source, algorithm, and reward function.
Right, and it's how these three pieces interact that really determines how a model learns. So the data source, that's like the raw material, the stuff the AI actually trains on.
And they found that using online sampling of data was way more effective than offline.
Exactly, because when the AI generates the data itself, it's constantly getting new examples.
It's a more dynamic learning process. So then there's the algorithm, which is like the engine, right? The method that uses the data and rewards to compute the gradients.
And this is where we saw that GRPO really shines. It uses the reward signal in this really nuanced way.
It's not just saying right or wrong, but giving a more detailed level of feedback.
And finally, we have the reward function, which is how the AI knows if it's doing a good job. The better the reward function, the better the AI learns.
And that's the area where they see the most potential for future research. Things like generalization, uncertainty, and those process rewards.
So all three of those, the data, the algorithm, and the reward, they all work together to determine how the model is trained. It's like a recipe, and you need all the ingredients to get it just right.
And understanding this unified paradigm, it helps us see how techniques like SFT, RFT, DPO, PPO, and GRPO, they all fit together and differ from each other.
Yeah, it's not just a bunch of random methods. They're all part of the same overall process of reinforcement learning. It also lets us evaluate which parts have the most impact on the model's performance.
It helps us see that reinforcement learning enhances performance by making the output distribution of the language model more robust, particularly in achieving the correct answer from multiple attempts.
And it highlights some key areas where we can improve these algorithms, like focusing on the data source, developing more robust algorithms, and improving reward functions.
I hope that explanation of a unified paradigm makes more sense. Let me know if you have any more questions about that.
I know, where were we? Oh yeah, we were talking about the impact that DeepSeekMath could have.
We were just starting to get into the potential downsides of AI.
Right, and how we need to be mindful of the risks as we develop this technology.
So we were saying that things like job displacement were a valid concern, but that AI could be more of a tool than a replacement.
Exactly, augmenting human capabilities and not necessarily replacing them entirely. Kind of like the invention of the calculator.
Didn't get rid of the need for mathematicians, it just freed them up to focus on more complex things.
And it'll be the same with DeepSeekMath. Some tasks will be automated. Oh yeah, let's hear it.
Thanks for your explanation. So can we compare RFT, DPO, PPO, and GRPO?
That's a really interesting observation and a great question. Let's dive into the details and compare those different methods.
Absolutely. It's important to understand how these different training approaches work. It'll give us a better sense of why GPO is so effective.
So you're asking specifically about fine-tuning, or FT, DPO, PPO, and GRPO, right? We touched on this earlier when we were talking about the unified paradigm.
Right. And it's like we were saying, these methods all fit within that framework. It's all about the data source, algorithm, and reward function.
So let's start with fine-tuning, or FT. That's like the most straightforward approach, right?
Yeah, FT is really just about taking a pre-trained model and then tweaking it on some specific data to make it perform better at a certain task.
So it's like taking a general purpose math student and training them to be really good at, like, calculus.
Exactly. But it's still kind of limited. It doesn't really have that reinforcement component, so its performance is ultimately limited by the quality of its training data.
Okay, that makes sense. Now, what about direct preference optimization, or DPO?
DPO is a bit more nuanced. It starts with the idea of having different outputs that are ranked by preference.
Right, so like one output is better than another.
Exactly. And the model is then trained to favor the better outputs over the worse ones. It does this by maximizing the probability of those preferred responses.
So it's like giving the AI a clear signal of what good looks like.
Yes, and that signal guides the model's learning. It's kind of like comparing two different paths to a solution and focusing more on the right one.
Okay, and that's also more advanced than just fine-tuning, because there's an element of that reward signal.
You got it. And now Proximal Policy Optimization, or PPO. PPO also uses a reward model, but it's more complex.
It needs a separate critic model, right?
That's the key difference. A value model is trained alongside the policy model, and this critic model estimates the value of the AI's actions.
And then it uses that estimate to tweak the AI's behavior, encouraging it to make better decisions.
Precisely. It's a very robust approach and has been very effective with language models, but it's also really resource intensive.
Right, it requires a lot of computational power. Which brings us to GPO.
Exactly. GPO is like PPO, but without that separate value model, it estimates the baseline reward from a group of outputs.
So instead of a critic, it's like a team of AIs all trying the same task and comparing results.
It's more efficient as it doesn't need to train a separate value model. It's also better at leveraging reward data, which can come from human comparisons or from model-based rewards.
So it's kind of like streamlining the whole reinforcement learning process.
Yes, all of these methods are aiming to improve the language model's ability to solve tasks, but they differ in how they use the reward signal.
Okay, this comparison make it much more clear. Fine-tuning is the most basic, DPO is a bit more advanced, TPO is powerful but heavy, and then GRPO is both powerful and efficient.
Exactly, and the researchers found that GRPO consistently outperformed the other methods.
It's a great example of how the right algorithm can make a big difference. Thanks for the question.
And if that clarifies the differences between those methods, then let's move on.
All right, so where were we?
Oh, go for it.
Thank you. Can we just wrap up and give the key takeaway for this paper?
Absolutely. I understand you're looking for the key takeaways, and we can definitely wrap things up with a focus on that.
Yeah, no problem at all. We can totally pivot to that now and hit the high notes.
So, to quickly recap, we've seen how DeepSeekMath is a powerful open source model.
And the main thing that makes it so special is that they use that huge, carefully curated data set, the DeepSeekMath corpus.
Right, and it was built using an iterative process of filtering and data selection.
And their interesting finding that ArcSieve papers were not very useful for improving math abilities, that was pretty wild.
Absolutely. It really underscores the importance of data quality and careful data selection.
Then we dove into how DeepSeekMath uses this new reinforcement learning technique, the GRPO algorithm.
And that GRPO is a clever, more efficient way to train the model by doing away with the critic model used in PPO.
Making it much faster and more efficient while still getting these major performance gains.
So the core takeaway is this: DeepSeekMath is showing us what's possible with open source AI.
And that these clever training methods can make a big impact.
And to really get the most out of these big models, it's not just about throwing massive data sets at them.
It's also about things like high quality data and smarter algorithms.
And that, like we discussed, there are all of these ethical considerations when talking about something this powerful.
Absolutely, we have to be responsible and always prioritize human well-being.
So as we move forward with AI, we need to keep learning, keep questioning, and keep working toward positive outcomes.
And it's a constant process of evaluation and adjustments where everyone gets involved.
It's a conversation and a future that we're all building together.
Ah, yeah, uh-huh.
Yeah, in addition, I saw the unified paradigm, the unified
You're bringing up
freedom.
another key aspect of the research. That's great.
Yeah, it sounds like you're noticing something in the paper about the experiment. Oh, go for it.
The high-level intuition of this RL is based on these unified paradigms. So we can
That's a fantastic way to put it. You're right. At a high level, it's about understanding how the unified paradigm informs our intuition about reinforcement learning.
Exactly. And I think that's a really insightful way to frame it. So the whole idea of the unified paradigm is, to help us understand how all the different pieces fit together.
It's about understanding the core elements: data source, algorithm, and reward function, and how these influence the whole process of RL.
Right. And when you really get what's happening with each of those elements, you can kind of start to anticipate how changes in each one are going to impact the overall outcome.
It gives you a more intuitive understanding of why some approaches work better than others, like why GPO is more efficient than PPO.
Yeah, you kind of get this feel for how the model is learning and why certain tweaks can be beneficial. Oh, you're diving into the core of it, right? The high level intuition, the big picture.
Yeah, you're picking up on something really important, which is the relationship between reinforcement learning and this unified paradigm.
Okay, so let's unpack this a little more and really focus on how the unified paradigm provides an intuition about reinforcement learning.
So remember the three components of this unified framework: the data, the algorithm, and the reward function.
Those all connect to the way that reinforcement learning works at a foundational level.
Yes, and the unified paradigm helps us understand how different RL techniques fit in, like GRPO, PPO, and DPO.
It's not just a random collection of methods, they're all part of a bigger process.
And it helps us identify the areas where we can make the biggest impact for model performance.
For example, the research suggests that the reward function is a crucial place to make improvements in the future.
Yes, and that's because it shapes the whole learning process of the AI.
So the better the reward, the more effective the training.
Exactly. And it also matters how you generate the training data for the AI. And the key is that this is not some black box. By understanding that unified framework, you can start to develop an intuition about what should work.
It's like, you understand how the pieces fit together so you can start to see the bigger picture and make better predictions.
Absolutely. And it also helps you develop better intuition for future AI research.
So yeah, I think that's a very good point that you make. And it's a key takeaway from all of this that we should remember.
And now, to pick up where we left off, it's worth remembering that it's not just about the overall benchmarks.
Right. They also look at performance on specific types of math problems too. And with this new lens, that's where we saw that online sampling is way more effective than offline sampling.
Yeah, it's a more dynamic process because the AI itself is creating that data.
It's actively exploring rather than just going through a preset list of examples.
And it's where algorithms like GRPO fit in because they enhance the way that the model learns from its mistakes.
So with this unified paradigm, we can really understand the big picture of how these different techniques all fit together.
It lets us see how GRPO, which was used with DeepSeekMath, is an improvement over previous methods as it relates to the data, algorithm, and reward functions. like the different domains, algebra versus calculus, it really digs into the areas where the model does well.
So when you look at all of that together, you can really get a sense of the body's strengths and weaknesses.
And it helps, understand where there is room for improvement.
It's always useful to analyze the data in multiple ways.
Absolutely. It helps to get a full picture.
Always great to have you join in with your insights. It really makes the whole show better.
So that's a wrap for this episode, and we hope to see you again next time.
Keep learning and keep exploring, and we'll catch you next time.
That brings us to the end of our show for today. Thanks for joining us, and we hope you found this discussion as enlightening as we did.
You can see how all these different things relate to how a model is trained and why it performs the way it does.
And it gives a clearer view of the potential for future research that could make the entire process even better.
So I think what you are picking up on is how the unified paradigm gives us a more intuitive understanding of how all these pieces interact and how that applies to RL.
I hope this clarification provides you with an even better understanding.
So with all that, where were we?
Oh yeah, we were about to move on to your last request, which was about the main takeaways and the guilt.
Right, let's quickly wrap things up and focus on the key points from this paper.
So we've established that DeepSeekMath is this really impressive open source model.
Yeah, and it was trained on that enormous DeepSeekMath corpus, 120 billion math tokens.
And they created that corpus by iteratively selecting high-quality math content from the Common Crawl.
And they had that pretty unexpected result that ArcSieve papers were not helpful at all.
Absolutely, which proves that data quality is essential when training these models.
And DeepSeekMath is also using this innovative GRPO reinforcement learning algorithm.
Right, and the key insight is that GRPO eliminates the need for a separate critic model, which makes it way more efficient.
So the big takeaway for this, DeepSeekMath is demonstrating the power of open source AI.
And that it's possible to improve performance through clever methods and not just by scaling up.
You really need both high-quality data and clever algorithms.
And like we've discussed, we need to always think about the ethical issues when working with AI this powerful.
For sure, we have to keep our responsibilities in check and make sure we keep human well-being in mind.
As we move into this new world of AI, we have to continue learning and questioning and making sure we're all moving forward toward positive outcomes.
And that it's a continuous process of learning and adapting where we all have a part to play.
It's a future that we're all making together, and it's still very much a work in progress.
And that we are still in the early stages of this AI trajectory with lots more to learn.
Okay, and I think that hits the key ideas you were interested in.
Yeah, I think so too. We've covered so much ground in this episode. It's been a very insightful conversation.
Absolutely. Thanks for joining us for this very in-depth look at DeepSeekMath.
And again, thank you so much for all your questions, your feedback, your insights, everything.